Carboxylic acids are acidic, as the name implies. That means that the proton that's in red there is easily removed, and once it is removed, it forms the carboxylate anion. So you may have this water that is present, and the water is going to go fishing for this hydrogen, and these electrons go on to the oxygen, which gives the minus here, so we get this H2O plus the extra proton that we picked up. So this is a general acid-base reaction. The carboxylic acid is acting as the acid, while water is acting as the base, which picks up the proton. So in this next reaction with acetic acid, which is the acid part, sodium hydroxide is acting as the base, and that sodium hydroxide, the OH minus part, is going to grab this hydrogen. These electrons go on to here. So we have the oxygen from acetic acid, there's a minus charge, we have the hydrogen, and then the OH from the sodium hydroxide. And with this minus, it's counterbalanced by the sodium ion. So this is sodium acetate. So carboxylic acids are pretty weak acids, and they can react with bases such as sodium hydroxide, potassium hydroxide, sodium bicarbonate, and sodium carbonate. So in the example of propanoic acid, the propanoic acid part is acting as the acid, potassium hydroxide is the base. So we can go fishing here for this hydrogen. We get the O minus, the hydrogen to the OH part of the potassium hydroxide. The potassium will counterbalance the carboxylate, so this would be named potassium propanoate, and that is going to be a salt. So what products are formed when benzoic acid is treated with sodium hydroxide? Benzoic acid, if you recall, is the benzene that has the carboxylic acid on it. We're going to react it with sodium hydroxide, which is Na plus OH minus. So the carboxylic acid will lose its proton and become the anion, which will counterbalance with the sodium ion. And then we have the OH from the sodium hydroxide, which paired up with the hydrogen from the carboxylic acid. Carboxylate anions are salts of carboxylic acid. So octanoic acid with a base. We have the O, it becomes O minus, Na plus, and water. So octanoic acid is not water soluble. The acid has more than 5 carbons, so it's insoluble in water. But when we make it a salt, the ionic salt is soluble in water. Okay, so we're going to look at these and label them as water soluble or insoluble. This benzoic acid derivative, which happens to be meta-ethyl benzoic acid, has greater than 5 carbons for carboxylic acid, so this is not. But the salt here of that version is, so this is H2O soluble. And butanoic acid has less than the 5 carbons, it has the good ratio, so this one is also water soluble. So to name carboxylate anions, we name the metal ion, parent name with the number of carbons, and we change the ic to 8 ending. So kind of like esters, except instead of the alkyl group, we use this ion. So this is sodium benzoate. And if you're looking at some of your food labels, you may actually see sodium benzoate used as an ingredient. This one inhibits the growth of fungus, and it's a preservative in soft drinks. This one over here is commonly known as potassium sorbate. And that's an additive that prolongs the shelf life of baked goods and other foods. So a lot of these salts are water soluble and they're used as preservatives. And then we're asked to draw the structure of sodium propanoate, another preservative used in baked goods. Propane is 3 carbons, and it has the O, and then there's a sodium on the other side of that, so it's Na+. So soaps are made of salts that are carboxylic acids that have many atoms in a long hydrocarbon chain. So you can see the structure of a soap here. This part is hydrophobic, so it does not like the water. But this side over here loves water. And that part is the water-soluble part. So the brown lines are the nonpolar tails, and the green is the polar heads. They form these micelles where it's all polar on the outside, so water surrounds it, and then there's the greasy nonpolar tails inside. Once you have these nonpolar hydrocarbon tails on the inside, the polar parts on the outside, it allows the water to go inside to surround all of the grease, and then the grease gets trapped inside the micelle and then can get rinsed away. So the water can get inside and clean up the grease. Aspirin we saw the structure of earlier. The active ingredient in aspirin is actually acetyl salicylic acid. The structure is similar to salicin, which you can see here. That is isolated from willow bark. Salicylic acid also comes from meadowsweet blossoms. So previously, people would use willow bark and boil that down into a tea and drink that. But the salicylic acid and then also the sodium salicylate salt that came from the meadowsweet that you see here. So the combination of those different teas would cause a lot of bad side effects, including irritated mucous membranes of the mouth and the stomach. And so in 1899, Felix Hoffmann developed the synthesis of acetyl salicylic acid. So instead of this salicylic acid or this compound from the willow bark tree, which all have this part in common or some form of it, he put an acetyl group on here and made it into an ester. Can be used to relieve pain and has less side effects. So after ingestion, aspirin travels into the stomach and then into the intestines, which has an acidic environment. The aspirin travels there in its neutral form. So you can see the neutral form in the gray box there. It can then enter the small intestine, which has a basic environment, and gets converted to the carboxylate. So a proton gets removed from that carboxylic acid right here. In the intestines, aspirin will exist as the ionic form, which is more soluble in the blood. And in order for it to give us pain relief, it has to get protonated to have the anti-inflammatory effects as well. To convert carboxylic acids to esters and amides, we're going to do a substitution reaction. So we start with this basic formula here where Z can equal an OH, OR prime, or NR prime 2, and Y is going to replace Z. And here Y equals OH, OR prime, or NR prime 2. So in the situation where we're going to make an ester, we're going to react it with an alcohol to give us the OR here. So we'll make an ester, and we have an OR prime plus our side product of water. So the OR prime is going to replace the OH. We get an ester here. And this is the reaction that's happening. We're going to squeeze out a water. And the same thing is going to happen with the amide formation. We're going to squeeze out a water and replace the NH2 with that carboxylic acid with that OH. So this is our amide. So the NH2 replaces the OH there. When we're looking at ester formations, we can use a specific reaction which is called the Fischer esterification, and this involves using a carboxylic acid and an alcohol in the presence of an acid. So our carboxylic acid in this situation is acetic acid, the alcohol is ethanol, and this is our catalytic acid. And catalytic just means that we use a small amount of it. And in all of these reactions where we're making esters, our water is going to be a side product. When I look for my carboxylic acid, I'm going to line it up with the OH of the ethanol part, and I'm going to look to remove this water molecule. So then when I draw my molecule, I have that part from the carboxylic acid. I form a new bond. This is the OCH2CH3 that forms as a result of that. So this is my ester, and our side product is water. In the reaction with benzoic acid and methanol, we have the carboxylic acid that's lined up with the methanol part. I'm going to look for my water molecule and remove that. So here's my benzoic acid. Then I have OCH3 plus water as a side product. When we're forming esters, the equilibrium is driven to the products by removing water. So sometimes we can put little beads in there that will soak up the water, and that will push the reaction to move towards the product side. Ethyl acetate is used in non-acetone nail polish remover. This is ethyl acetate, which is used in non-acetone nail polish remover. So another look here at these reactions, you have a carboxylic acid. We're going to remove this OH part. So these two things form water. So remove the OH of the carboxylic acid and the H from the alcohol, and we form the ester plus HOH. So that red bond to the OR group is our new bond. So if we did this reaction again, it's easiest to see when you have your OH lined up with the alcohol part. We have O to CH3 plus H2O. And if you wanted to draw out your atoms this way, you could for your CH3 or CH3CH2. That's another way of drawing that. All right, in our practice problem, what ester is formed when each carboxylic acid is treated with ethanol in the presence of H2SO4? So we're going to do this reaction with ethanol, which has 2 carbons. And one of the things that I'm going to do to make my life a little bit easier is to draw out this carboxylic acid. So I'm just going to rewrite the reaction down here. So it's just a cyclohexane with the carboxylic acid. So the CO2H is a carboxylic acid. I think that it helps to visualize the reaction better when you can see all of the atoms drawn out, or at least the ones that are important in the reaction. So we have H2SO4 here. So I'm going to look for my OH from the acid and the H from the alcohol, which is right here. And then you're going to take that out and squeeze the other 2 molecules together. So my new bond is right there, and then I had the bond to the OCH2CH3. So that's the ester that I'm going to make in that reaction. Now we can do the same reaction with benzoic acid. So look for your water, OH and then H here. All right, and in both cases, if you want to draw out your water that is the side product, you can do that, but you don't have to. Identify A in the following reaction. A was converted in one step to that compound that I won't try to pronounce, the sex pheromone of the female German cockroach Blatella germanica. So we're looking for A. We have alcohol here. Here's our alcohol part. This is the carboxylic acid. So I'm going to look for my water to squeeze out. So I take the OH from the acid and the hydrogen from here and then squish those together. There's the acid part. Here's my new bond. I have an O, and then the rest of it is the benzene ring. So that would be A. That's the ester that we formed for A. And then at some point this gets reduced. Then we form these 2 carbonyls from where the ethers were, and our benzene becomes, or a quinone,